Ohm's law. Okay, so we're going to start with the vocabulary. When there's only one path in my circuit, we call the circuit a series circuit. Okay? So far in class, prior to spring break, all we have done has been series circuits. Just like in math class, when you have a series, it's just a list of numbers. They come one after another. Okay? Same thing here. They go one after another until you get back to where you started. Charge is a conserved quantity. Alright? In a closed system, it must be conserved. Now, my circuit, there's nowhere for those electrons to go other than around the circuit. Alright? So, therefore, current must also be conserved. Now, if there's only one path, the current has to be the same all the way around. There's nowhere for it to go. Okay, so we've seen this a couple of times in class. When you add more batteries, what you're doing is you're adding more voltage. We're not going to study it specifically, but if you put two batteries in series, you add up the voltages, right? We saw that a little bit today in class. If you had two D batteries, you had 1.5 volts in each, so you had 3 volts total. Okay, back to Ohm's law. When you had more voltage, the bulbs got brighter. So we decided in class that we could write this as a proportionality. That voltage is directly proportional to the current. Alright, when you add more bulbs, we saw that the bulbs got less bright each. Okay. So we can write that as proportionality as well, but this time it's not a direct proportionality. Now, resistance is proportional to 1 over the current. Right? The other way to say that is that they're inversely proportional. But I don't like that. I don't know how to combine that one with the other one. So I'm going to algebraically rearrange it. I'm going to say that the inverse of the resistance is proportional to current. Alright, if they're inversely proportional to each other, it doesn't matter which way I write it. Alright, but now I have two proportionalities that have currents on that right-hand side. So just like an equation, I can combine them. Alright, and we come up with this. That voltage over resistance is proportional to I. So the purpose of the lab today was to make sure there wasn't some coefficient in there. So that's what we did. Alright, so what we were looking for is something called Ohm's law. Alright, this is the driving equation in circuits. Pretty much, if you're going to analyze a circuit, you're going to use Ohm's law somewhere. It's not a bad one to have memorized if you want to memorize equations, but you don't have to. It's on your equation sheet when you get it. Alright, so what is Ohm's law? Okay, so for materials that are ohmic, Ohm's law applies. What that means is if they follow the equation, they're ohmic. Yep, it's a circular definition. Go with it. Alright, so again, this is for ideal materials, because nothing is truly ohmic under all conditions. Alright, but it's experimentally true enough that most conductors we use in circuits are close enough. Here's the equation. It's pretty simple. V equals IR. Alright, remember that V is your voltage. Okay, so if you see it on the equation sheet, you still have all those equations at the top from electrostatics, where V could just be potential. But it's a current. It's a circuit. There's got to be a delta V in there, so it's really that voltage. Okay? But remember, us physicists are lazy. We drop the delta. Okay, so I said we're going to use Ohm's law all the time. Okay, so I can apply it to single circuit elements. Okay? I can look at one little piece of the circuit, and I can use Ohm's law to analyze that. Here's an example problem. I have a 10 ohm resistor that has a current of 2 amps through it. What is the voltage drop across it? Okay, so I haven't put fancy animations in, but I'm solving for my voltage. Okay, that's V. I know my resistance, R, and current, I. My equation is V equals IR. Well, that one is already solved for V. So I just take I and R and I multiply them together. My answer is 20 volts. Alright, I can also use Ohm's law for an entire circuit. I can use it for part of a circuit that's not just one element as well, but we don't have anything that we're going to deal with that yet. We'll do that after spring break. For right now, we're going to keep it simple. Okay, so for this entire circuit, I have a 12-volt battery and 1.2 amps of current. And I want to know what is the total resistance in that circuit. Okay, so my driving equation is V equals IR. When I solve that for R, I get V divided by I. Okay, that's not too bad. So I take 12 divided by 1.2 and I get 10. So my answer is 10 ohms. Alright, so that last question talked about total resistance in a circuit. Okay? Now, in a series circuit, that's not too bad. And I'm going to give you the equation here in a second. Alright? So, when they're in a line, when they're in series, the resistors, they just add up. Okay? We can think of resistors as an obstacle to the flow of current. So if I have to hit one wall, and then I make it through, and then I hit another one, and I make it through, and I hit another one, well, I've had to deal with all three. Okay? So they just add up. The sum of the resistors in the circuit, or again, in part of a circuit, we'll deal with that after break. Okay, that sum is called the equivalent resistance. What that means is if, say I had three resistors in a line. Okay? They're in series. We just add up their numbers. Well, that's the equivalent resistance. So what that means is that I could take those three out and put one back in with the equivalent resistance. And to everything else in the circuit, it would look the same. Okay, so here's my equation. The equivalent resistance, now this is for resistors in series, remember, is R1 plus R2 plus R3 if it's there, plus however many more you want to put in the line. Okay? That's it. So, one last practice problem. Okay, what is the equivalent resistance of a circuit with a 12 ohm resistor in series with a 6 ohm resistor and a 2 ohm resistor? Alright, now I know I just add up their values. So 12 plus 6 is 18 plus 2 is 20. Alright? And it's still resistance, so it's still in ohms. So that's my answer. Alright, that's it for all our equations and concepts before break. You have a practice problem set. We'll deal with it after break. I will be putting up some solution videos for some of those problems over break. You don't have to watch them, but if you want to, they're there. Alright. I will see you guys after break.